Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. I'd like to welcome you to our webinar on mastering complex processes with design of experiments. This has been planned in conjunction with JUMP, whose software you may already use to make your experiments far more efficient. And also we have a guest speaker from Symrise, who is joining us to talk about how they use DOE, or design of experiments, to understand complex processes in targeted formulation development. Now, before I tell you more about the topic for today, I'd like to tell you a little bit about the software and a couple of housekeeping notes. So the software we're using is GoToWebinar. You may have used this before, but the most important bit for you in this is the questions box. So there's a box towards the bottom of the panel on the right-hand side of your screen. You can move that around to wherever you feel most comfortable. But if you have any question at any point throughout the presentation, then just type your question in there and we will do our best to get to it at the end of the presentations. If we don't have time, don't worry, we'll send them all on, and if there is an answer for you, then we'll try and get it to you. So do please get your questions in there as we go along. We're also going to ask a couple of polls to try and get to know a bit more about you. Now, these polls seem to work best when it's not full screened, but do feel free to engage with those polls. Let us know a bit about you. It helps us to tailor the webinars to make sure that we're giving you the right sort of information, and it may help in any follow-up, then we can make sure we're getting you the answers to your questions at the right levels. Now, this is being recorded, so there will be a video made available to you in a few days' time. So if there's anything that you miss, or your connection drops out, or you'd like to just come back and watch again, then that recording will be sent to you by email and you'll be able to watch it at leisure. For that reason, we tend not to share the presentations for these, because we think the most important thing is not just what you'll see on screen, but also the words that our presenters are saying. So do keep an eye out for that email in case you want to review anything that you've heard. Also, everybody who attends live, and there are lots of you, can see there's still a few coming in, everyone who attends live will get a certificate saying that you attended this live as a little thank you from us. So in today's webinar, we're going to learn how Symrise's approach in design of experiments leads to better understanding of complex processes and targeted formulation development. By the end of the webinar, which will last about an hour, you should learn how you can use design of experiments and modeling techniques to create improved process understanding, to achieve faster and more targeted experimental product development, and to help subject matter experts make decisions based on good quality data. We have two guests with us today. A little bit later on, we'll be joined by Egon Gross from Symrise. He's an engineer in biotechnology and works in the research and technology department of Symrise AG. They're a global company in the flavour and fragrance business. He's been using design of experiments approaches and principles for well over 7 years, as often as possible, to speed up development tasks and to obtain more insight into the systems of interest. Before him, we'll hear from Florian Voigt, who is a systems engineer for JUMP. He is based in Germany, and before joining SAS, which is JUMP's parent product, he worked as a process engineer in research and development. He did process optimization, product development, process evaluation. So he's exactly the right person to know how this sort of software and this sort of approach can help you to get the most out of your own chemical processes. Thank you once again to JUMP for helping us to get in touch with Florian, and for also helping us find Egon, as well as identify a topic that we think is of particular interest. And I can see from the number of people who turned up that they were clearly spot on. So thanks to JUMP for that. So the next thing for me to do is to hand over to Florian. So we should hear and see Florian, and we'll hand control to him and he can pick up from there. Thank you once again for joining us. I hope you enjoyed the webinar. Do get your questions in, and we'll make sure that we'll answer as many of them as we possibly can at the end of the webinar. Florian, thank you for joining us.
Thanks, Ben, and welcome everybody joining before, during, or maybe also after lunch. Thanks for taking your time listening to today's webinar on mastering complex processes with design of experiments. For today, we have three topics, and I will cover the first two, and the main part will be the third one, covered by Egon Gross. And first of all, I'll give you a short introduction to design of experiments and what the advantages are. And then I will do a quick case study using JUMP software and do some design of experiments. And then Egon will present how he is using and adapting design of experiment methods in JUMP to understand their processes at Symrise. So what will you learn today? first of all, you will have an answer to the question, what is design of experiments? And also, what are the advantages of applying design of experiments? And then you learn two methods or designs that can be used to cover most of the experimental needs using JUMP. And then finally, you'll hear a large practical example for the successful application of design of experiments brought to you by Egon. So before we start into the topic, I would like to have you think about why experiment? And of course, it's most of the people's job to do experiments, but what's the purpose behind? And that is not only to get good results or to achieve good results, but it's also to get bad results. So the short answer is to create understanding. And here I would like to recommend an article that a colleague of me has written some time ago. He's called Phil K, and you can find this article on LinkedIn. If you search why experiment and Phil K, or just scan that QR code. And he has written a great article on exactly this question, why experiment? Okay, so now before we start with the content of the presentation, I would like to start with our first question in the first poll.
Thank you very much, Florian. So what we're going to do now, we will ask you a poll question. So our cameras should disappear and the poll question should appear on the screen for you. So is design of experiments used in your organization at the moment? And if not, why not? It's a reasonable spread. I'm pleased to see a quarter of our audience are already using DOE as a standard data collection approach. A further quarter are using it as sort of special circumstances. But resoundingly, 43%, almost half of the people that voted, just don't know how to apply design of experiments approaches. Now, that means you're in exactly the right place and you're talking to exactly the right people, because not only are Florian and Egon going to show you the benefits, but also walk you through some of how you can actually achieve those benefits. We'll close those poll results now and hand back to Florian. And Florian can carry on with the presentation.
Thanks for answering the poll. It is great to hear that so many people use it already as a standard and or use it at all. That is great. But what we hear quite often is that we don't know how to apply it. And I'm happy to actually see that almost nobody answered that they don't see the benefit. So we work on the how-to today. But to get a short distinction of what design of experiment is compared to fairly widespread conventional method called one factor at a time, I will present you this here. So with one factor at a time, you are generally fixing all factors and only varying one factor per experiment. So in this case, I'm showing here, we have a combination of pH value and temperature. And just from our prior knowledge, we fix our pH value at, let's say, 6.8, and then we start varying temperature, and we increase it per experiment. And then at some point, we find a maximum at just below 60. So we'll fix the temperature and we continue experimenting, and now we only vary the pH value. And then at some stage, we find that at a pH value of roughly 7.2 and a temperature of just about 60 degrees, we have a maximum yield. And we assume that this is the optimum. But we're not sure that this is really the optimum, because as you can see, that there's a lot of white space in here. And what the problem is with this approach is that we assume a certain behavior of the two parameters, temperature and pH. And if that behavior was the case, so that we had just a single peak, then we would have found the maximum, but we do not know. It could also be that the true behavior of the interaction between temperature and pH is rather a bridge than a peak. So with one factor at a time approach, we're not really able to securely identify the true behavior of such a system. And a solution to this was invented many years ago, and that is design of experiments, which is basically a structured investigation of the whole experimental space. So if we take a look at the combinations of pH and temperature, this example of a 3x3 factorial design results in 9 experiments. And as you can see here from this plot, they cover all of the experimental space. And what we also notice is that this corner combination that we hadn't covered with our one factor at a time approach is covered, even though there might be a few more percentiles that we can optimize. We would have made a large benefit compared to the one factor at a time. So if we compare the numbers for that one factor at a time result, we made 14 runs and ended up with a roughly 60% yield. And with this designed experiment, with only 9 runs, we ended up with more than 90% of yield. So we had more yield with less effort. And a great analogy that I heard just a few weeks ago was one factor at a time is like looking through a keyhole into a room and trying to see everything that's in there, whereas design of experiment is just like opening that door and going into the room. So think about that for a second, and I would ask Ben kindly to prepare the second poll.
So, what are the most important aspects of conducting experiments for your company? Just pick one of these. And most people, perhaps predictably, it's for all of the above. The point of conducting experiments is a mixture of all of these, of getting quick, reliable, optimized, and fully understood results about your processes.
Great, thanks, Ben. So yes, 55% want to have all of the above. And basically, those are the aspects that are covered or can be achieved by using design of experiments. So now we would like to look a little bit deeper into experimental design. And I will just quickly show 2 experimental goals and the designs that are used to achieve these goals. And for one, it's typically a first step, or maybe also only one step. A goal is to identify important factors. So if you don't know much about a process, at first hand, you want to know which are the factors in my process that have most effect on the outcome. And then a second step could be, once you know these, or maybe already in the beginning, you want to optimize your process. So these are 2 steps that can be either achieved by sequential experimenting, so doing first an identification of factors, doing screening experiments, and then do optimization once you have identified the important factors. Or, and that is something that I want to introduce to you today, is there's a class of experimental designs called definitive screening designs, and they can cover both in one step, saving you even more time and money by achieving comparable results to a sequential experimenting. And the reason why I'm presenting this is because Egon has made a practical experience with those and is using them in his daily work, and will show an example later on. So if we look at what JUMP offers in design of experiments, there's specifically 2 platforms which cover most of the demands for experimental design. And one is the just mentioned definitive screening designs. So these are ideal for screening situations where you don't know much about your process initially. And for almost all other situations, we have a platform called custom designs. There you can add almost any situation and get the design matching to your situation in the lab, other than trying to find a design that matches your experiment. So those are the two platforms, and we will now go into the JUMP software and take a look how that can be done in practice. So I'll just move over to JUMP and show you how you can work there, and also show you the difference between the two-step approach and definitive screening designs. So we've just learned what is design of experiments, and the case study that I have brought to you is basically a simple chemical process with 5 factors and 1 critical output, 1 response. And we're now looking at the 2 scenarios. And the first scenario is the two-step approach with screening and augmenting. And the third approach is the second approach is the definitive screening design. So for this process, we have a response, which is our output. It's called critical output characteristic. We want to maximize it. And we also have our factors, and these are pressure, modifier, agitation, temperature, and time. So if we want to do a classical approach, set up a screening experiment, we could use the custom design platform in JUMP. In the DOE menu, you find it right on top, and you will find this user interface where you can add your responses and your factors. And if you have your responses already in a table, you can just go and load these into this interface. And the same is for your factors. You can also load your factors into this interface. And then you have it already integrated with your response, your factors, and by default, you get the main effects model. And below here, you can specify how many runs you would like to do, so how many experiments. And there's 3 options. The minimum is what's mathematically necessary to do a model. So we have 5 factors and the intercept, so we need at least 6 experiments. And then there's a default, which is a suggestion made by JUMP in order to compensate the noise. But you can also specify if you, let's say, want to have more or less, depending on your capabilities. You can specify how many runs you want. If you click Make Design and then Make Table, you will end up with a table that has a experimental plan. So we have 12 runs in this case, and here we have the settings, and here we have a column where we can enter the result once we have done the experiments. And we also have readily prepared some buttons with play buttons here, and that is the model. So JUMP automatically creates the model based on what we have specified, so that once we have collected the data, we can just analyze it by clicking this play button. I'll show you that. I've also prepared this table with some results in. So just data table here. And now we have the table with the results. And if we then just click this button, we get the results I want to show you. So here we have, based on this experimental plan and the results of the critical output characteristic, we have those factors shown here that have an influence on our response. We also have a p-value which indicates how important each factor is. Much more informative is what's called prediction profile that you see down below here. And that is all the factors that have an influence and how they influence the critical output characteristic in a visual and interactive way. So that means I can now click and drag this red line here, and by that change the value of one parameter. And as you see, while I change it, it also changes the other factors, but most importantly, I can see how it affects the critical output characteristics of my response. So I can simulate, if I would use other values for my factors, how that would affect my critical output characteristic. And of course, I can let also jump calculate what would be the combination of my factors that would yield the highest value for the critical output characteristic. So now we've done that, and you see the factors that have an influence on our critical output characteristic, but you also see that this model is not very accurate yet. So you might want to follow that two-step approach that I've introduced before, and you want to make this more meaningful and build on what you have done before. That's what we call augmenting a design. So that is available just in the DOE menu here. And then you have this interface where you can select those parameters that you want to further investigate. We can just say, well, we want to investigate all. And this is still our critical output characteristic, our response. We hit OK. If we wish, we can now adjust the experimental space. And if we then click Augment and Make Design, again, Make Table, we will get a table that contains all of the experiments and results that we had before, but just added some additional to make the model more meaningful. I also have prepared this with results, and I would like to show you. So from the screening experiment with 12 runs, we have added 6 more runs here, and we have now performed the experiments and have the results there. And if we now take a look at the result that is coming from this, then we see that we have less factors, but we also have interaction terms, so interaction between modifier and temperature, and also quadratic terms for the factor time. And also notice that the width of the confidence intervals is much lower. And if we now move the red bar, you see that while moving it, the slope of the other bar is changing. So that is the interaction between modifier and temperature. And from the curve in time, you see the quadratic effect. So let's now go and maximize this. We'll end up with 82% here. And that is the result from an 18-run two-step approach with screening and augmenting. So I'll keep this in the back here for a second. And now we'll take a look at definitive screening designs. So you find these as well in the DOE menu, definitive screening design. If we just take that table here, we have 5 factors. So we will end up with 13 runs that we have to do. And if we now take a look at the results for the definitive screening design, we see that looks very, very similar to the two-step approach with augmenting. So we have almost the same effect summary here. We have the interaction effect. We also have the quadratic effect. And the model, if we maximize it, see, has a similar output, which is only very, very a little lower than with this approach. And compare that to 13 versus 18 runs. So to summarize that, design of experiments helps to find the true behavior of a system that we're investigating. And especially if you don't know much about your process, definitive screening designs can reduce the amount of experimental work significantly. And if you look at this case with 5 factors, we had almost the same results with 30% less experiments. So that is very great, and we do recommend to use this if it is applicable for you. And we will learn a little bit more about definitive screening designs and how they are applied from Egon. So now, question 3 from Ben, please.
So what do you consider to be the biggest hurdles when using design of experiments? This won't add up to 100% because you can tick more than one box, but it does seem that the biggest hurdle there is not having the necessary knowledge. Is that sort of what you expected to see, that it's a mixture of those different hurdles that people have to get over in order to start using a design of experiments approach?
Yes, many people seem to be afraid a little bit of getting started because they fear that they don't have the necessary knowledge. So other than that, I hope that this example encourages to just get started and start doing it.
I have to say, I've been really impressed with the range of different resources that Jump put out and the community around Jump products as well. So even if it's a question that you don't put Jump themselves, the Jump user community is really good. There's lots of good discussion about how to make the most of that and how to really improve your efficiency. So have a look at Jump's website. Come and join us in the webinars with Phil Kay. That's the best way to learn more about this sort of thing. And of course, we're about to learn even more with Egon Gross. So Egon's camera is live now. Florian, thank you ever so much. And we shall hand over to Egon now to pick up on how Symrise use design of experiments principles in order to speed up development tasks, obtain more insight into their systems of interest. So thank you very much, Egon.
Hello, everyone, and I'm happy to introduce you to our experiments we made and to get you to know what we are doing here at Symrise with design of experiments and other things. But before we go into the case study, I want to introduce you a little bit to our company so everyone knows who we are, what we do, and then we switch to the case study. So Symrise was founded a long time ago. The first foundation was in 1874 with the formation of Harman and Reimer. And then several years later, Dragoco joined in the local vicinity. And since 2003, both companies were joined. And then since then, we are under the name of Symrise, growing organically and with acquisitions. We are located worldwide. As Ben said, our headquarters is in Holzminden in Lower Saxony. There are other main hubs, one in France, in Marlow, one in France, one in New York, in Teterboro, one in Sao Paulo, and the other one in Singapore. Beside these 4 main hubs with research and development departments, there are several others, even down to distribution locations. Symrise is separates within 3 segments with flavors, with nutrition, and with scent and care. And they even break down deeper to the core market they are dealing with. For example, for flavors, it's beverages or sweet or savory. In the scent and care part, it might be active ingredients for skin protection, for sun protection, for consumer fragrances, or for menthol and things like that. As we are located worldwide, the locations have a different input to the sales contribution. It's about 4% in North America, around 13% in Latin America, 4% in Europe, Middle East, and about 7.5% in Asia Pacific. So the emerging markets represent quite a lot share of our sales and income. Within the flavor market, which is at about 500 billion, Symrise has a share of about 10%. And with the other three competitors, Firmenich, IFF, and Givaudan, we are dealing for about 50% of the global market. So now to the case study where we use JUMP. The shown example is a development of a biocatalysis. It also could be used for an optimization process. And here is a rudimental scheme of a chemical reaction. It's two components are brought together, and with the aid of the enzyme, we get then to the product and maybe a side product. And as we are working with biocatalysis, we are involved with living systems that might be cells or enzymes. And so beside the chemical aspects, we have to deal with biological aspects in order to optimize the desired reaction. So in this case, we are dealing with 4 continuous variables, being, for example, time, temperature, pH, concentration of whatever kind, what you can imagine, what could be continuous. 3 categorical variables, might be a supplier, might be a different raw material, or things like that. And from these categorical variables, we have 2 at 2 levels and 1 at 4 levels. And while creating the design of experiment plan, we then saw that we could not run all the required experiments during one day, but during 4 days of work. So we thought about that in advance and took the day also as variable into account, in this case as a blocking variable, to see, because we were curious to see if the day might have an impact, which we hoped it would not. And therefore, we ended up with a DSD approach of around 30 runs, or as an alternative, the custom designer, resulting in 46 runs for only interactions. And if we would then add up to response surface model, being able to model the curvature, we would have done 80 experiments. So based on the variables and the levels of interest, the custom design fits best, but we have to invest a lot of time and money to do those 80 experiments. On the other hand, the standard DSD approach, which Florian showed, is only valid for 2-level categorical variables. And in our case, we had one which we wanted to investigate at 4 levels, and the other, the day, which then came by as a side effect also for 4 levels. And to overcome this hurdle, there was a reach deep into the trick box, and this was supported by Peter Hirsch from JUMP to overcome the limitation of the definitive screening design. And with this, we go to JUMP, and I then created to start with you the journey for a definitive screening design with this kind of table, which Florian already introduced. So we have our continuous variables being on a level of -1 and +1. This could be any figure being representative for this variable, being meaningful. Then we have a categorical variable stated cat A and B. The second one was cat C and D. And then we had our variables which we want to combine in the cat E1 and E2 and cat E3 and E4. And during the process of the building of the design, the day also came in. So the easiest way is then to go to the DOE, to definitive screening design, and then to load the factors in this table. So this is a common starting point. If you are doing an experiment, you first think of what you want to do. For example, I just show you how to get to a table like this. You might think of continuous factors, but not only one, but for 4 factors. You can name them whatever you want. You put your minimum and your maximum level in. If you have other types, a discrete numeric might be a gear shift, gear 1, 2, and 3, or you have categorical variables on different levels. And if you then say save the factors, you have like a table like this where all the information is stored. So it's very easy to get a basic table where you can then start on making different designs and afterwards comparing your designs before you start work. So as we have now our factors all in a table, we then go to continue in the DSD platform, and we want to get the center runs to estimate the quadratic effects. By default, we have 2 blocks or even more, depending maybe on the days you want to or you have to run the experiments, and then you can add some extra runs. Here I went to 8 extra runs, giving more a degree of freedom for the interactions or the quadratic effects, which then might be possible. And after hitting Make Design, you have the first glance of the design table. You can analyze it before you make your final table. You see how the correlation pattern is. So the definitive screening design has in general no correlation within the main effects and all the interactions. In this case, you see a slight correlation between the main effects. This comes because we are here in the range of the categorical variables. So there is some minor interaction maybe, and because we don't make so many runs. And then to come to the final table, it's wise in this case not to randomize within the blocks, but to completely randomize the table and just hit Make Table. Then we have our working table where we can start on. And so we see we have our 30 experiments being in 2 blocks, which we don't consider for now. And here we have our 4 continuous variables, our 2 two-level categorical variables, our 4-level variables to be. By the time now, it's only on 2 levels. And with this tool, you see very easily how the table consists, which are the connections to the rows and to the labels. And now, in order to combine these into one variable having 4 levels, we go to the column menu, to the utilities, and say combine columns. Then we type in the name we want and delimiter, which makes life easier afterwards if you want to separate it again, and hit OK. And now you see L1, L2, underscore L2 comprises of L1 cut 1 to 2 and L2 from cut 3 to 4. So with this interaction, you see the scheme very easily. And to use meaningful abbreviations, we then can hit the right mouse button and go to recode these elements in whatever is meaningful then to you. And then here you see that a new column is made out of this recoding process. We could also select in place, but to see it better, I'll leave it at new column and go to recode. So we get a new column. Oh, here I made a mismatch, a type mismatch. So I delete this column. I recode it again. And now I have it in a proper order. I want it. So it's A, B, C, and D. And to see it in a better way, we can order the bars by name, and we have it alphabetically ordered. So out of these variables, 2 variables on each 2 levels, we made 1 variable at 1 level. And the same process I did for day, which is already done. And this is the table. It's the exact copy where I did this day thing again, this recoding thing. And you see for the first day, there's a certain pattern on the experiments you have to do. For the continuous variables, they are all in for the first day. And the 2 categorical variables are also in. The second day has a little other picture, so the mean point is not in there. And the third day is also lacking the mean point. And in the fourth day, we have the mean point again. So this is the general setup for the experiment. And after performing these 30 runs with our settings, we ended up in 2 parameters we wanted to invest, named Y1 and Y2. And so for now, I want just to show you the way to make a model out of Y2. And Florian mentioned that it's quite easy if you build your model and you have your experiments. You just hit the play button to make your model. But as you see here, nothing happens. Why? Because we customized the DSD, making out of the 2-level categorical variables a single categorical variable with 4 levels. So the workaround would be either to make a generalized regression, either for both individually or for one at the row, and then go to the next variable, making your model. Within this platform, We can choose the distribution, and we can choose the way we want to build the model. And there are also validation methods available. And just by hitting Go, JUMP creates a model with 9 non-zero parameters. And then you can look for different models, let them run, and then evaluate your models based on the factors you need, based on the R square or whatever parameter you want. And that's quite easy forward. And then you can argue with the models and see what's meaning this model, what's meaning that model, what's the outcome, does it make sense from a physical, from a chemical point of view. And so based on this, I made a model which is here presented. You see the actual by predicted value, an R square value of 0.99, which is quite nice. You see the slope and the points. You see your factors with a p-value, and all these factors are highly significant. And here you can then customize your model. If there should be a contribution which is not significant, you just can click and remove it. Or if you were not sure, you just undo it, and so you can customize your model and tune it. So beside this actual by predicted plot, you see a lot of different other plots which are meaningful by the time you get to know them. So the residual versus the predicted plot, or the studentized residual, where outliers are easily to be detected. You get your scaled estimates, and last but not least, you get your profiler, which Florian also already introduced. So you see there is an effect of the continuous one variable on our y. And as I move the red bar, you see the shape changes for cut E1 to E4, but there is no change for the day 1, 2, 3, 4. So in this case, we wanted to optimize it. We go to the desirability function. This is the optimization direction, and say then maximize desirability. And these would be our settings for the best experiment out of these runs, and to start augmenting the design in this region for higher values for cont 1 or lower values for cont 4 with the cat 1, maybe cat 2, but the cat 1 seems to be the best. Which was very astonishing was that the day had such a big effect of our outcome. If we would not have taken this into account from the beginning, it would have seen like this. So on the left-hand side, you have already the known graph from actual versus predicted of our final optimum model. And this is the same methodology behind, but without the day as variable parameters. And here you see the spread is far bigger. And if we want to see why this comes, we just click in the graph, say row legend, and go to the cut. By default, we have the same shape, but different colors. We can switch even to different shapes, solid or not. And as these are from the same data table, the points are interacted. So everything I mark here is also already shown in any other graph of a analysis from the same data table. And we see with cut E1, there is a spread over the whole range from the lowest to the highest values. E2 is only more in the above section. E3 is medium to low performance, and E4 is even lower until medium performance. So with E1, we have the biggest spread of our data. And just by looking at this graph without the knowledge that the day is effective in a way, one might be sufficient and happy with this R square, not knowing that there is something in behind, which can lead to a far better understanding of the process. And as we addressed the day as a possible effect and introduced it from the beginning, we were at once capable to see this factor, to see the outcome, instead of here, without the day, where the confidence intervals are far bigger. And as you see with the cut E1 to E4, also there are far bigger confidence intervals than using the day, because this unclarity of the day is somehow incorporated in the other four factors. In case this would be not sufficient for the experimenter, he either would go into the data and dig deep and looking what is in, or he would be sufficient and losing a factor. In our case, as this effect is not the one an experimenter wants, because on every day the results should be comparable and not such a big difference, we had the possibility also, after digging into the data, to find an effect which then led to these degrees of yield at this specific experiments during the day 2, and then we could identify the root cause and skip then the further or modify our further processes. And with these learnings, I then go back to PowerPoint and finalize our results. So the outcome was a successful identification of significant influential parameters, main effects and interaction effects. We saw significant differences in the variable E1 till E4, which we would expected. But the day, as I mentioned, was not expected. It was not intended to have an influence. And by using this in the background, we were then able to identify the root cause. So coming to the summary, the DOE approach was very helpful and powerful for us in order to detect the significant parameters at once in one step with an according experimental setup. And JUMP offers far more possibilities than the design of choice and the definitive screening designs, like standard textbook designs, Plackett-Berman, fractional factorial, split box designs, central composite designs, and a lot of more. And by the DOE approach, we were prompted to think about the setup and the potential outcome before we went to the lab and made any experiment. And it was, in our case, also possible to customize the standard DSD approach far more to our needs. So these day procedure or behavior led then to more process insight, and all this work was done, as you saw, within a week. thinking before what makes sense, where are the limitations, what's the maximum, what's the minimum. And after having the results, it was quite straightforward and easy and fast to get all these nice curves and insights into the data. So this was my contribution to this web. And now I hand over to Ben.
Thank you very much, Egon. Fascinating. It's really interesting to see how much you can pick up, and so quickly as well. But let's dive into some of these questions then. Amal El Gabawi has asked, he said, we usually start with a one factor at a time approach in our study. How much do you think, knowing that there are alternatives, is that a waste of resources? Florian, maybe start with you for that one.
Well, yeah, I think that going back to the analogy that I just recently learned, the problem is that you're not knowing where you're actually moving. So the thought that doing one factor at a time to sort of get an orientation first is quite often misleading, and I think that's the answer. So you don't know if you're really looking at the right spots of your room, if you think of like this small keyhole. Whereas if you start with thinking about all the factors that could potentially affect your response, and then do an experimental design, you will open that door, and then you will see. And that's I think, yeah, I think that would be my answer to it. Is really a waste of experiments.
So there we go. So it's always best to sort of take that step back and see the bigger picture, as it were, rather than trying to peer through that keyhole. We've had a couple of people asking similar questions, so I'm going to wrap them up into one. So Janil and Radhima have also asked, how do we get our hands on the software, and on what platforms does it work? Does it have to be the latest version of Windows, or is it a bit more broadly applicable?
Well, there's a quick answer to that, and I can just pop it into the chat as well.
Thank you.
Just have to select. So we do have all the system requirements on our webpage, and I've just sent around a link. So basically, it's running on Windows, it's running on Mac. Yeah, and the specific requirements you can find there. And if you want to just take a look and try Jump, you can just go to the website jump.com, and there you'll find a button to download a 30-day trial version. Or if you're already convinced you want to have the software, you can also buy it right there and download it from the website.
Of course, if you are planning on attending the webinar in June, or the webinar series in June, then we'd encourage you to get the trial version and have that enabled and on your system before you start with that, because you will get to have a go at it in real time. But that trial is, it's very generous of Jump to offer the free trial, and it really will help you see quite how useful this can be to you. So let's dig into another question. So one here from, there's lots of them coming in now, which means I'm starting to get a bit lost in them. From Ivan Oparo, who said, is a DOE approach to all different types of scientific experiments? So if you're looking at fabrication of conducting polymer fiber via wet spinning methods, can you still use a DOE approach to make sure that you're getting the best of that?
Well, if I can start answering to this, yes, that is applicable for any scientific experiment that you can think of, really. A lot of customers do use design of experiments for actually production processes. So yes, that is certainly possible.
Excellent. Thank you, Ivan, for your question as well. One thing that often comes up in this is this still an applicable approach if your product is a mixture? And how do you handle the product being a mixture when you're designing your experiments and also reviewing the results?
So maybe I can give the short answer. there's a design called Mixture Designs that is specifically there to create experimental designs for mixtures. Maybe Egon has also thoughts on this, because I think you're using Mixture Designs or have been using them.
Yes, I have been using them, as our formulations are very often mixtures. But if I have the freedom to break these mixture behavior open, it runs in far more insight, because if you take a mixture into account, if one concentration goes up, other concentration have to go down to meet your 100%. And if you look at it from another perspective, to break it open and say, okay, I can vary all my, or at least some variables independently, you get a far more better insight into the data. And afterwards, if you're composing it, you already run up to 100% in the sum. So it's another way around to look at the same problem.
Excellent. I think we've probably pushed it about as far as we can go now. We've gone nearly 10 minutes over, but thank you very much, Florian and Egon, for sticking around for that extra time, and to the audience as well for staying with us and asking those excellent questions, even after we'd technically run out of time. I do hope I haven't kept anybody from their lunch or from any other important meetings. So that is it for today's webinar. Thank you once again to Florian and to Egon for joining us from Jump and Symrise, respectively. Thank you to Jump as well for putting us in touch with Florian and Egon, and for pointing out this as an important topic that the chemistry community can learn a great deal from. So we work with Jump on a great deal of things, and they're always an excellent partner, always coming up with interesting ideas. And the number of people who turned up today have clearly proved that that was the case. So once again, we will send a recording and a certificate to everybody who has attended. So that will be with you in a few days' time if you wanted to go back and rewatch any part of this. So that recording will be with you soon, and you can pick it all up. Thank you once again to Florian and Egon. I'm Ben Valsler, Chemistry World's digital editor, and we will see you again for the next Chemistry World webinar. Thank you ever so much.